In computer science, program optimization or software optimization is the process of modifying a software system to make some aspect of it work more efficiently or use fewer resources. In general, a computer program may be optimized so that it executes more rapidly, or is capable of operating with less memory storage or other resources, or draw less power. General. Although the word optimization shares the same root as optimal, it is rare for the process of optimization to produce a truly optimal system. The optimized system will typically only be optimal in one application or for one audience. One might reduce the amount of time that a program takes to perform some task at the price of making it consume more memory. In an application where memory space is at a premium, one might deliberately choose a slower algorithm in order to use less memory. Often there is no one-size-fits-all design which works well in all cases, so engineers make trade-offs to optimize the attributes of greatest interest. Additionally, the effort required to make a piece of software completely optimal, incapable of any further improvement, is almost always more than is reasonable for the benefits that would be accrued, so the process of optimization may be halted before a completely optimal solution has been reached. Fortunately, it is often the case that the greatest improvements come early in the process. Levels of optimization. Optimization can occur at a number of levels. Typically the higher levels have greater impact, and are harder to change later on in a project, requiring significant changes or a complete rewrite if they need to be changed. Thus optimization can typically proceed via refinement from higher to lower, with initial gains being larger and achieved with less work, and later gains being smaller and requiring more work. However, in some cases overall performance depends on performance of very low-level portions of a program, and small changes at a late stage or early consideration of low-level details can have outsized impact. Typically some consideration is given to efficiency throughout a project, though this varies significantly, but major optimization is often considered a refinement to be done late, if ever. On longer-running projects there are typically cycles of optimization, where improving one area reveals limitations in another, and these are typically curtailed when performance is acceptable or gains become too small or costly. As performance is part of the specification of a program that is unusably slow is not fit for purpose. A video game with 60 Hz is acceptable, but 6 FPS is unacceptably choppy. Performance is a consideration from the start, to ensure that the system is able to deliver sufficient performance, and early prototypes need to have roughly acceptable performance for there to be confidence that the final system will achieve acceptable performance. This is sometimes omitted in the belief that optimization can always be done later, resulting in prototype systems that are far too slow, often by an order of magnitude or more, and systems that ultimately are failures because they architecturally cannot achieve their performance goals, such as the Intel 432, or ones that take years of work to achieve acceptable performance, such as Java, which only achieved acceptable performance with Hotspot. The degree to which performance changes between prototype and production system, and how amenable it is to optimization, can be a significant source of uncertainty and risk. Design level. At the highest level, the design may be optimized to make best use of the available resources, given goals, constraints, and expected use load. The architectural design of a system overwhelmingly affects its performance. For example, a system that is network latency bound would be optimized to minimize network trips, ideally making a single request rather than multiple round trips. Choice of design depends on the goals. When designing a compiler, if fast compilation is the key priority, a one-pass compiler is faster than a multi-pass compiler. But if speed of output code is the goal, a slower multi-pass compiler fulfills the goal better, even though it takes longer itself. choice of platform and programming language occur at this level, and changing them frequently requires a complete rewrite. Though a modular system may allow rewrite of only some component, for example, a Python program may rewrite performance-critical sections in C. In a distributed system, choice of architecture occurs at the design level, and may be difficult to change, particularly if all components cannot be replaced in sync. Algorithms and data structures. Given an overall design, a good choice of efficient algorithms and data structures, and efficient implementation of these algorithms and data structures comes next. After design, the choice of algorithms and data structures affects efficiency more than any other aspect of the program. Generally, data structures are more difficult to change than algorithms, as a data structure assumption and its performance assumptions are used throughout the program, though this can be minimized by the use of abstract data types in function definitions, and keeping the concrete data structure definitions restricted to a few places. For algorithms, this primarily consists of ensuring that algorithms are constant O, logarithmic O, linear O, or in some cases log linear O in the input. Algorithms with quadratic complexity O fail to scale, and even linear algorithms cause problems if repeatedly called, and are typically replaced with constant or logarithmic if possible. Beyond asymptotic order of growth, the constant factors matter. An asymptotically slower algorithm may be faster or smaller than an asymptotically faster algorithm when they are both faced with small input, which may be the case that occurs in reality. Often a hybrid algorithm will provide the best performance, due to this trade-off changing with size. A general technique to improve performance is to avoid work. A good example is the use of a fast path for common cases, improving performance by avoiding unnecessary work. For example, using a simple text layout algorithm for Latin text, only switching to a complex layout algorithm for complex scripts, such as Devanagari. Another important technique is caching, particularly memoization, which avoids redundant computations. Because of the importance of caching, there are often many levels of caching in a system, which can cause problems from memory use, and correctness issues from stale caches. Source code level. Beyond general algorithms and their implementation on an abstract machine, concrete source code level choices can make a significant difference. For example, on early C compilers, while was slower than for an unconditional loop, because while evaluated one and then had a conditional jump which tested if it was true, while for had an unconditional jump. Some optimizations can nowadays be performed by optimizing compilers. This depends on the source language, the target machine language, and the compiler, and can be both difficult to understand or predict and changes over time. This is a key place where understanding of compilers and machine code can improve performance. Loop invariant code motion and return value optimization are examples of optimizations that reduce the need for auxiliary variables and can even result in faster performance by avoiding roundabout optimizations. Build level. Between the source and compile level, directives and build flags can be used to tune performance options in the source code and compiler respectively, such as using preprocessor defines to disable unneeded software features, optimizing for specific processor models or hardware capabilities, or predicting branching, for instance. Source-based software distribution systems such as BSDs, ports and Gentis portage can take advantage of this form of optimization. Compile level. Use of an optimizing compiler tends to ensure that the executable program is optimized at least as much as the compiler can predict. Assembly level. At the lowest level, writing code using an assembly language designed for a particular hardware platform can produce the most efficient and compact code if the programmer takes advantage of the full repertoire of machine instructions. Many operating systems used on embedded systems have been traditionally written in assembler code for this reason. Programs are seldom written from start to finish in assembly due to the time and cost involved. Most are compiled down from a high-level language to assembly and hand-optimized from there. When efficiency and size are less important, large parts may be written in a high-level language. With more modern optimizing compilers and the greater complexity of recent CPUs, it is harder to write more efficient code than what the compiler generates, and few projects need this ultimate optimization step. Much code written today is intended to run on as many machines as possible. As a consequence, programmers and compilers don't always take advantage of the more efficient instructions provided by newer CPUs or quirks of older models. Additionally, assembly code tuned for a particular processor without using such instructions might still be suboptimal on a different processor, expecting a different tuning of the code. Typically today, rather than writing in assembly language, programmers will use a disassembler to analyze the output of a compiler and change the high-level source code so that it can be compiled more efficiently, or understand why it is inefficient. Runtime. Just-in-time compilers can produce customized machine code based on runtime data, at the cost of compilation overhead. This technique dates to the earliest regular expression engines, and has become widespread with Java Hotspot and V8 for JavaScript. In some cases, adaptive optimization may be able to perform runtime optimization exceeding the capability of static compilers by dynamically adjusting parameters according to the actual input or other factors. Profile-guided optimization is an ahead-of-time compilation optimization technique based on runtime profiles, and is similar to a static, average-case analog of the dynamic technique of adaptive optimization. Self-modifying code can alter itself in response to runtime conditions in order to optimize code. This was more common in assembly language programs. Some CPU designs can perform some optimizations at runtime. Some examples include out-of-order execution, speculative execution, instruction pipelines, and branch predictors. Compilers can help the program take advantage of these CPU features, for example through instruction scheduling. Platform-dependent and independent optimizations. Code optimization can be also broadly categorized as platform-dependent and platform-independent techniques. While the latter ones are effective on most or all platforms, platform-dependent techniques use specific properties of one platform, or rely on parameters depending on the single platform or even on the single processor. Writing or producing different versions of the same code for different processes might therefore be needed. For instance, in the case of compile-level optimization, platform-independent techniques are generic techniques that impact most CPU architectures in a similar way. Generally, these serve to reduce the total instruction path length required to complete the program or reduce total memory usage during the process. On the other hand, platform-dependent techniques involve instruction scheduling, instruction-level parallelism, data-level parallelism, cache optimization techniques, and the optimal instruction scheduling might be different even on different processes of the same architecture. Strength reduction. Computational tasks can be performed in several different ways with varying efficiency. A more efficient version with equivalent functionality is known as a strength reduction. For example, consider the following C code snippet whose intention is to obtain the sum of all integers from 1 to n. Int I, sum equals 0, for sum plus equals I, print. This code can be rewritten using a mathematical formula like int sum equals n asterisk 2, print. The optimization, sometimes performed automatically by an optimizing compiler, is to select a method that is more computationally efficient, while retaining the same functionality. See algorithmic efficiency for a discussion of some of these techniques. However, a significant improvement in performance can often be achieved by removing extraneous functionality. Optimization is not always an obvious or intuitive process. In the example above, the optimized version might actually be slower than the original version if n were sufficiently small and the particular hardware happens to be much faster at performing addition and looping operations than multiplication and division. Trade-offs. In some cases, however, optimization relies on using more elaborate algorithms, making use of special cases and special tricks, and performing complex trade-offs. A fully optimized program might be more difficult to comprehend and hence may contain more faults than unoptimized versions. Beyond eliminating obvious anti-patterns, some code-level optimizations decrease maintainability. Optimization will generally focus on improving just one or two aspects of performance: execution time, memory usage, disk space, bandwidth, power consumption, or some other resource. This will usually require a trade-off where one factor is optimized at the expense of others. For example, increasing the size of cache improves runtime performance, but also increases the memory consumption. Other common trade-offs include code clarity and conciseness. There are instances where the programmer performing the optimization must decide to make the software better for some operations but at the cost of making other operations less efficient. These trade-offs may sometimes be of a non-technical nature, such as when a competitor has published a benchmark result that must be beaten in order to improve commercial success, but comes perhaps with the burden of making normal usage of the software less efficient. Such changes are sometimes jokingly referred to as pessimizations. Bottlenecks. Optimization may include finding a bottleneck in a system, a component that is the limiting factor on performance. In terms of code, this will often be a hotspot, a critical part of the code that is the primary consumer of the needed resource, though it can be another factor, such as I/O latency or network bandwidth. In computer science, resource consumption often follows a form of power law distribution, and the Pareto principle can be applied to resource optimization by observing that 80% of the resources are typically used by 20% of the operations. More complex algorithms and data structures perform well with many items, while simple algorithms are more suitable for small amounts of data. The setup, initialization time, and constant factors of the more complex algorithm can outweigh the benefit, and thus a hybrid algorithm or adaptive algorithm may be faster than any single algorithm. In some cases, adding more memory can help to make a program run faster. For example, a filtering program will commonly read each line and filter and output that line immediately. This only uses enough memory for one line, but performance is typically poor, due to the latency of each disk read. Performance can be greatly improved by reading the entire file then writing the filtered result, though this uses much more memory. Caching the result is similarly effective, though also requiring larger memory use. When to optimize. Optimization can reduce readability and add code that is used only to improve the performance. This may complicate programs or systems, making them harder to maintain and debug. As a result, optimization or performance tuning is often performed at the end of the development stage. Donald Knuth made the following two statements on optimization. We should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil. Yet we should not pass up our opportunities in that critical 3%. In established engineering disciplines, a 12% improvement, easily obtained, is never considered marginal, and I believe the same viewpoint should prevail in software engineering. Premature optimization is a phrase used to describe a situation where a programmer lets performance considerations affect the design of a piece of code. This can result in a design that is not as clean as it could have been or code that is incorrect, because the code is complicated by the optimization and the programmer is distracted by optimizing. When deciding whether to optimize a specific part of the program, Amdahl's law should always be considered. The impact on the overall program depends very much on how much time is actually spent in that specific part, which is not always clear from looking at the code without a performance analysis. A better approach is therefore to design first, code from the design, and then profile, benchmark the resulting code to see which parts should be optimized. A simple and elegant design is often easier to optimize at this stage, and profiling may reveal unexpected performance problems that would not have been addressed by premature optimization. In practice, it is often necessary to keep performance goals in mind when first designing software, but the programmer balances the goals of design and optimization.